is Dr. V.C. Sontake, Assistant Professor in the Department of Mechanical Engineering, St. Vincent Pallotti College of Engineering and Technology, Nagpur. I am going to teach the course Heat Transfer. Following are the objectives of this video lecture. The first objective is the definition and significance of thermal conductivity. Second objective is to define homogeneous and isotropic materials. And third objective is to explain thermal capacity and thermal diffusivity and its significance as far as heat transfer study is concerned. So let us start our discussion with thermal conductivity, its definition, significance, and characteristics. Thermal conductivity, K. From Fourier's law of heat conduction, the rate of heat transfer by conduction can be given by the equation Q is equal to minus K A into dt by L in watt or joule per second. So let us take the solid material having thickness L, area A normal to heat transfer, its two phases at temperatures T1 and T2 respectively, such that T1 is greater than T2. So whatever rate of heat transfer takes place from this phase to this phase is given by this equation. In this equation, K is a constant of proportionality and is also called as thermal conductivity of the heat conducting material. So thermal conductivity will be the property of this material of which this solid is made up of. Rearrangement of this equation for K will give me this expression. Small k is equal to minus Q into L over A into dt. So this is the equation of thermal conductivity for K from Fourier's law of heat conduction. In this equation, if I put the unit of Q as watt, L as meter, A as meter square, and unit of dt as degree Celsius or Kelvin, the unit of K comes out watt per meter degree Celsius or watt per meter Kelvin. So we can take either of the unit. One more thing, whether you take watt per meter degree Celsius or watt per meter Kelvin, the magnitude is not going to change because here we are considering temperature difference rather than absolute temperature. So whether you take degree Celsius or K for temperature difference as a unit, it hardly matters. Further, from equation 4.2, K is equal to minus Q into L over A into dt. In this equation, if I put L is equal to 1 meter, A is equal to 1 meter square, and dt is equal to 1 degree Celsius or Kelvin, then Q is equal to K. Now, what is the meaning of this mathematical term K is equal to Q? So, meaning is this: from here you can define thermal conductivity. So, thermal conductivity of material is defined as the amount of energy conducted in unit time, that is rate of heat conducted, through a solid body of unit area and unit thickness when the temperature difference across its phases are maintained at unity. Now what does it mean actually? So let us consider once again this solid. Let's say in this solid, if I maintained its thickness L is equal to 1 meter, the area normal to the heat flow as 1 meter square, and temperature difference across these two phases as 1 degree Celsius, By virtue of heat transfer, by virtue of temperature difference, heat transfer will take place from left to the right phase at some rate. That rate of heat transfer is called as thermal conductivity for this solid material. Now to elaborate this further, area into length will give me volume of 1 meter cube. So what does it mean? If you take a cube of volume 1 meter cube and maintain temperature difference across its two faces as 1 degree Celsius, such that T1 is greater than T2. So whatever heat transfer takes place across the faces of that cube of unit volume, that heat transfer rate will be the thermal conductivity of the material of that cube. So that is its interpretation, or that is how thermal conductivity is defined. Thermal conductivity is also defined as the ability of the material to transfer heat by conduction. It signifies the easiness with which heat can be conducted through solid body or material. Now mind well, the simplest definition ever. It defines the easiness with which material allows heat to conduct it through it. More easily it allows heat to be conducted through it, its thermal conductivity is high. More difficult, it offers more difficulty in conducting heat, its thermal conductivity value is low. So material with high value of K is called as good heat conductor, and material with low value of K is called as poor conductor of heat or good heat insulator. Now in this diagram, thermal conductivity values are given in this table in the numerical forms, and ranges of thermal conductivities for different materials are given in this diagram. Now as you can see here, sorry for the inconvenience. Okay, so as you can see here in this chart, the diamond is having highest thermal conductivity. However, diamond is not metal. It is a non-crystalline, non-metallic crystal. Then followed by silver, copper, gold, aluminium, iron, and carbon steels. So metals are having highest thermal conductivity with the exception of some non-metallic solids like diamond. Followed by non-metallic solids. So we have this material brick. Its thermal conductivity is 0.720 watt per meter Kelvin. Then in liquid, water is having thermal conductivity of 0.556 watt per meter Kelvin, and gases, air is having thermal conductivity of 0.024 watt per meter Kelvin. So thermal conductivity decreases in this order. Similarly, in this diagram, as you can see here, the thermal conductivity value varies from 0.01 watt per meter Kelvin, which is lowest value for gases, and some non-crystalline metals, diamond, graphite, silicon carbide, and quartz are having highest thermal conductivity of 1000 and in this range. However, Metals are having highest thermal conductivity in their purest form, but these four non-crystalline metals are the exceptions, followed by metal alloys, then non-metals, liquids, insulators, and least value of thermal conductivity for gases. Now let us discuss some of the factors upon which thermal conductivity depends and its variation. So thermal conductivity of the material or substance depends upon the following parameters. Material structure like chemical composition, physical state and texture, moisture content, density of the material, and operating conditions of pressure and temperature. All these factors, some or the other way, affect the thermal conductivity of the material. Let us discuss some salient points about thermal conductivity and its variation with respect to these parameters. The decreasing order of thermal conductivity in different materials are as follows. Pure metals will have highest thermal conductivity, then metal alloys, non-metallic crystalline and amorphous substances. Exceptions are diamond, graphite, silicon carbide and quartz. Then liquids and least value for gases. Thermal conductivity of a material is the result of migration of free electrons and vibration of lattice structure. This vibration of lattice structure is nothing but physical interaction of molecules as a result of this lattice vibration. In metals, molecules' activity is smaller due to their closely packed nature, and hence flow of free electrons are responsible for thermal conductivity of metals. So basically there are these two phenomena. Either heat transfer by conduction takes place by free electrons or by vibration of lattice structure or physical interaction of molecules. So in metals, the first factor will be predominating. So thermal conductivity of metals is basically due to free electrons. And this phenomena in metals is also called as electron drift. Whereas in case of fluids like solids, liquids and gases, free electron movement is very small. So the first factor is not very dominating. And thermal conductivity is due to the frequency of interactions between the lattice atoms or molecules. So in case of fluids, the lattice vibration of the structure takes place, and by virtue of this, molecules come into physical contact and heat transfer takes place by conduction. So for fluids, thermal conductivity is due to lattice vibration. Pure metal is having highest thermal conductivity. Their thermal conductivity decreases if they become alloy metals, and presence of impurities in metal causes decreasing in their thermal conductivity. For example, copper is having highest thermal conductivity. But the moment copper and zinc are mixed to make alloy metal, their thermal conductivity decreases. Mechanical forming processes such as forging, drying and bending or heat treatment of metal causes considerable decrease in the thermal conductivity of materials. For example, thermal conductivity of hardened steel is lower than that of the annealed steel. So these mechanical processes also affect the thermal conductivity of the materials. Now, effect of temperature. Temperature is the very important parameter which affects the thermal conductivity of the material to a greater extent, and its effect is different on different types of materials. So let us discuss its effect on different types of materials, starting with metals. For most metals, the value of thermal conductivity decreases as the temperature increases. Exceptions are aluminum and uranium. So metal will have good thermal conductivity at room temperature. The moment you increase their thermal conductivity, decreases. The moment you increase the room temperature, their thermal conductivity decreases. And you decrease their temperature, the thermal conductivity will increase. So this is room temperature. Let's say I am considering copper. So if you increase the temperature above room temperature, K will be decreasing. If you decrease the temperature below room temperature, there K will be increasing. So the lower will be the temperature, highest will be the thermal conductivity of metals. For the thermal conductivity of non-metal increases due to increase in the temperature. So there is a direct relationship for non-metals. More will be the temperature, more will be their thermal conductivity. For liquids, most of the liquids, thermal conductivity decreases as the temperature increases because of decrease in density, except water and glycerin. Their thermal conductivity increases with increase of temperature. Gases, as the thermal conductivity of gases increases with the increase of temperature, and it is proportional to the square root of the absolute temperature. Now what happens when you increase the temperature of gases? Their mean free velocity increases and they start moving at a high speed randomly, and under such condition their chances or probability of coming into contact increases, and hence heat transfer by conduction increases, so as the thermal conductivity. For most of the materials, thermal conductivity depend almost linearly on temperature. So we can give the relationship of or dependence of thermal conductivity on temperature for different materials by this equation, where K is the thermal conductivity at some temperature T, K0 is the thermal conductivity at room temperature, thermal conductivity at 0 degrees Celsius temperature. Beta is called as constant. It is also called as coefficient of thermal expansion. And its value depends upon the effect of temperature on thermal conductivity. For example, beta value will be positive if thermal conductivity increases with increasing temperature, such as for insulating materials and gases. Here K increases as T increases, and beta value will be negative when K decreases with temperature, such as for metal conductors and liquids. Then finally, thermal conductivity of solids and liquids weakly dependent on pressure and is independent of pressure for gases at nearly atmospheric pressure. So pressure is the parameter which does not affect the thermal conductivity to a greater extent. So this is all about thermal conductivity of different materials and its characteristics. Now let us define two different types of materials, isotropic and anisotropic materials, with regard to the variation of thermal conductivity in different directions. Now there are some materials whose thermal conductivity varies in the direction of heat flow. Their thermal conductivity does not vary with reference to the direction of heat flow. That is, their thermal conductivity will be constant irrespective of the direction of heat flow. Such materials are called as isotropic material, and their thermal conductivity will be constant whether the heat is flowing in x direction, y direction, or z direction. So such materials are called as isotropic material. Most of the engineering materials for practical purposes are considered as isotropic materials. Then comes anisotropic materials. So the materials whose thermal conductivity vary with reference to the direction of heat flow is called as anisotropic material. So their thermal conductivity will be different in different direction. Kx will be different, Ky will be different, Kz will be different. Such materials are called as isotropic materials. Examples of this material are wood, asbestos, some crystalline substances, laminated plastics, and laminated metals. For example, in case of wood, the thermal conductivity of the wood along the direction of grain and perpendicular to the direction of grain. So Kx will be more than Ky. Kx will be different, Ky will be different. That is why wood is an anisotropic material. Now these isotropic and anisotropic materials and their characteristics are very important as far as heat transfer studies are concerned, because these two types of materials are going to affect the heat transfer rate in different directions. So we must know the characteristics of these two materials. Now let us define another property called as thermal capacity. Thermal capacity of the material or substance is defined as the product of its density and specific heat of that particular material. Mathematically, thermal capacity is equal to rho into C, and its unit comes joule per meter cube Kelvin. Significance of thermal capacity. It indicates the heat absorbing or storing capacity of the material. More will be the heat absorbing capacity, more will be the thermal capacity. It also indicates the thermal inertia or sluggishness to conduct the heat by the material. For example, copper. Sorry, don't take the example of copper. If a material is having more thermal capacity, so what it will do, if a heat transfer is made to flow across its faces by virtue of temperature difference, what this material will do, since its heat storing capacity is high, it will start storing heat inside this and won't allow heat to be conducted. That means it will delay the process of heat conduction, or it will increase the sluggishness of the heat conduction across this material. So that is why thermal capacity indicates thermal inertia or sluggishness to conduct the heat. More will be the thermal capacity, more will be the storing capacity, and more will be the sluggishness to the heat conduction. Then thermal diffusivity represented by alpha. Thermal diffusivity is the ratio of thermal conductivity to the thermal capacity of the material or substance. Mathematically, thermal diffusivity alpha is the ratio of K by rho C, and its unit is meter square per second. Now here I bring to your kind notice one more property whose unit is same, and it is called as kinematic viscosity in fluid mechanics. It is also having the same unit, meter square per second. Many times this question is asked in engineering competition examinations for 1 mark. You remember. Significance. Thermal diffusivity is the property of the substance because it is the ratio of properties of the substance. K is also property, rho C is also property, so their ratio will also be property of the substance, that is alpha. Now, if any substance is having high value of thermal diffusivity, this high value of thermal diffusivity may result due to high value of K or low value of rho C. Now, what is the significance of high value of alpha? For example, metals are having high thermal conductivity and low value of rho C. So their alpha value will also be high. So what does it mean? Metals will be more interested or effective in conducting heat rather than storing it. So high value of thermal diffusivity means material will be more able to conduct the heat rather than storing it. Similarly, low value of alpha means it may result from either low value of K or high value of rho C. For example, liquids. Liquids have low value of K and high value of rho C. So they will be more effective in storing heat rather than conducting the heat across it. Something very interesting interpretation of or significance of thermal diffusivity. It indicates the rate at which heat is distributed in a material. Larger the thermal diffusivity, higher would be the ratio of change of temperature at any point in the material. Now, please correct it. In the unsteady state, temperature distribution is governed by both thermal conductivity as well as by thermal capacity. That is, unsteady state heat transfer depends on thermal diffusivity, whereas in steady state, the temperature distribution is affected only by thermal conductivity. And the final significance, the relative magnitude of thermal diffusivity is a measure of the rapidity with which the material responds to sudden change in the temperature of the surrounding. Metals and gases have relatively large value of alpha because of high value of K, and their response to temperature is quite rapid. Whereas the non-metallic solids such as solids and liquids respond slowly to change because of their relatively small value of thermal diffusivity. So, for example, let us take a room at 5 degrees Celsius temperature, and metal block is kept at 35 degrees Celsius and another non-metallic block is kept at the same temperature. Let's say temperature of the room is changed suddenly to 8 degrees Celsius. Now to this sudden change in the temperature of the room, Metal, because of their higher value of thermal diffusivity, will respond very fastly, whereas the non-metallic block will not respond as fastly as the metal does. So, as a result of this, temperature of the metal block will change faster as compared to the temperature of the non-metallic solid. So that is by virtue of this thermal diffusivity property. So with this, I come to an end of this video lecture. So after watching this video lecture, following are the learning outcomes. You will be able to define and explain thermal conductivity and its significance, and also the dependence of thermal conductivity and variation with respect to various parameters. You will also be able to define isotropic and anisotropic material. You will be able to define and explain thermal capacity and its significance. And finally, you will be able to define and explain thermal diffusivity and its significance. So with this, I come to an end of this video lecture. Thanks for passionate listening. Happy learning.